So actually what that whole problem is hinging on goes all the way back to this expression. So delta G and E cell potential relate to similar things, they're just in different situations. So delta G is typically looking at bond energies, so we're talking about joules or kilojoules, and our cell potential is looking at electron transfer. Electron transfer gets measured a different way, and I would bet ultimately why is just because they were discovered at different times. And so those individual pathways stuck, and then we're stuck with dealing with conversions between them. So that when we deal with delta G's, the default system was spontaneous, was negative, and we look at our cell potentials, our default situation is when they're positive. So we have to remember that those two things swap on us. So for a spontaneous reaction, we've got our negative and positive, and non-spontaneous is positive and negative. We do need to remember that and keep track of that. If we go back to your individual quizzes, you might notice, at least I did in grading, that there were several cases where you were losing minus signs and interpreting it incorrectly because you've lost that minus sign. This is something that's important that you need to keep track of to make sure that you're actually interpreting correctly. Kind of make sense? Of course, 8:30. What we're looking at is our cell potentials, and we need that larger, or in this case, if we're looking at the substance being reduced, must have a larger or more positive standard cell potential than the other. So if you made a battery using lead and aluminum, which one should be oxidized and which one should be reduced? Discuss at your tables. We're concerned about our lead and our aluminum, so what we should go through and identify would be our lead and our aluminum within this system. Okay, fun story. We've got a couple different places where lead shows up. There's one up there and there's one down here. Any bets which one you're supposed to be looking at? I would actually bet you're supposed to be looking at the bottom one. The only thing I'm going off of is if we look at the question, it doesn't refer to the ion, it's referring to PB with a 0. That might be a little bit thin or a tenuous argument, but I think that's the argument that we should be working with. And then we've got our aluminum here. So which one should be oxidized and which one should be reduced? Go ahead. Aluminum oxidized. What does oxidized mean? So when we're saying the aluminum should be oxidized, if we take a look at our cell potentials, those are reduction cell potentials, which means we need to flip that equation. So the suggestion is that our aluminum should be flipped to aluminum plus 3 electrons. If we go through and flip that, what happens to the cell potential? Okay. Because we're flipping that cell, or a reaction, we're also going to flip the cell potential. It changes. So we're taking a negative times the initial negative, 1.66 volts. And then we'd want to stack that with our lead, Pb plus our 2 electrons, goes to Pb metal. And our cell potential for the Pb metal is negative 0.13. So if we looked at the overall equation, we have, forgot the charge. Our Pp plus 2 plus our aluminum goes to our aluminum plus 3 plus our lead. Does anybody see any potential issues with this? What's the issue?
Not balanced.
Why is it not balanced?
The ionic charges between lead and aluminum on both sides don't match up.
So you actually said two things that would allow us to check this, which is fantastic. So number one, what we could go through and do is look at the overall equation in purple. Right? In the overall situation, our charges don't balance. Yeah. I've already committed to writing it out. Okay, so if we look at the left-hand side of the equation, we're at +2. We look at the right-hand side of the equation, it's a +3. Those charges don't align, okay, which means somehow or another we've got electrons either being produced or consumed in this overall reaction, which is problematic because we can't have electrons existing on their own, which means we didn't balance the equation, which means we have to double back and ensure we've actually balanced this appropriately. How can we go through and do that? If we go back to the half reactions, the half reactions at least show us those electrons and give us a little bit more flexibility to go through and balance. So what we could go through and do is multiply that top equation by 2. Why'd you pick 2?
Just to balance the not have 6.
So what we're looking at is the electrons transferred in the course of this reaction. Those electrons don't balance out appropriately. So to go through and balance them, what we're finding is the lowest common multiple between 3 and 2, which is going to come out to be 6. So that top equation, we'd multiply everything through by 2, and 2 times 3 would come out to be 6. What happens at the bottom? We're going to multiply everything through by 3. Okay. Now if we went through and added up our equations, we'd get 2 aluminum, we'd get 3 lead ions, 2 aluminum plus 3, and 3 lead. We should be able to go through and verify that that equation is indeed balanced by both looking at charges and our electrons. We just did it via electrons, so we can ignore the electrons and we can shift instead to looking at the overall equation for charges. We've got a +6 on the reactant side, and you have a +6 on the product side, which would show the equation's balance. Does that make sense?
Are there any trends in the hot reaction electrons, or is that something that's always going to be given to us?
What do you mean, as in the numbers?
Yeah, I mean, like
The numbers will be given to you.
Okay.
You're not expected to know those numbers, and there's not enough of a trend to be able to predict those out. Since you multiplied those equations, what should you do with the cell potentials? Why nothing? Or did you say nothing?
I said add.
So we could add these up, but again, back to my question, you multiplied this top equation by 2, right?
Oh, you should multiply those by 2. Is that what you're saying?
That's what I'm asking.
You should then. No.
I genuinely don't remember. But I kind of get the feeling you don't. Yeah, you're saying you don't? Okay. Can we get a second on that, just to confirm? In theory, you went through your Alex homework where you did this weekend. Okay? And I don't believe you do. Okay? So that means to get our cell potential, we just go through and add them up. We got a negative times a negative, which makes that a positive. So we got a positive 1.66 volts minus the 0.131 volts. Not the greatest with math. What are we, 1.53 volts? Positive. Okay, is this spontaneous? Delta G is supposed to be negative. Why are you telling me it's spontaneous? Okay, this goes back to knowing that equation. Okay, E cell will be positive for a spontaneous system. Okay, delta G will be negative. Okay, and that goes all the way back to the expression, which I'm pulling kind of from my memory, but wasn't that long ago. Negative NF or E cell. Okay. So for a delta G to be negative, we'll have a positive cell potential because N is the number of electrons transferred. That will always be positive, and Faraday's constant is also a positive value. Kind of make sense? What happens if you flipped the wrong equation? So can I erase the work? Yeah? I already forgot the equation we flipped. We flipped the aluminum, right? So let's flip the lead. What happens? Since we flipped the lead, what's its cell potential? become a positive 0.13. And what would the cell potential for the aluminum be? Negative, because we didn't flip it. When we look at our cell potential, what do we get? We get a negative value. That negative value is now non-spontaneous. Kind of, sort of? You also. Whoop, come on, pen. Not that button. So, our cell potential is affected by changing the conditions. So, temperature, we should already be aware of temperature affecting the conditions. Why should we be aware of temperature affecting the conditions? Say that again? Changes the equilibrium. That would change K. How many times have we seen K show up with our cell potential? We didn't. So why is changing the equilibrium matter? I completely agree with you. We're 100% right, but we haven't addressed it explicitly. We addressed delta G equals NF, our cell potential, right? Is delta G tied to K? Yes. How is delta G tied to K? I'm going to cheat because I don't remember it. Oh, I did remember it. That's nice. Negative RT, natural log of K. So if temperature is going to affect our rate constant, right, that will go through and also affect our cell potential. Right? pH. How could pH affect our cell potentials? Becomes a harder question, particularly because I don't think we talked about it in this class. We didn't talk about balancing under acid or basic conditions, right? I'm going to take that as a yes. We did not talk about that. Okay. We did a little bit on Tuesday, so we'll double back to the expression that brings it up. Sorry if you get dizzy. Close your eyes. If we look at this overall expression, or this overall equation, Tuesday noticed something that y'all did not. What do you think they noticed? Does anybody notice? Charges aren't balanced. Push deeper, because it's easier than that. Yeah, there's a whole hell of a lot of oxygens that we haven't accounted for. Right? I don't believe that Alex has asked about balancing under acidic or basic conditions. Is that true? Okay. And since the Alex homework was due this past weekend, I don't think you have to worry about it. But if you were going to go through and balance under acidic or basic conditions, okay, there are some other issues that we'd have to watch out for, but we'll real quickly walk through it. You would balance your oxygens by adding water to the side of the equation that was missing. Help me out. What do we got? 2, there's 8. So I'd need 6 to balance out those hydrogens. I would add, I can't do math real fast, but I'm assuming something like that. Okay, more or less. Don't stress about the logistics behind this. But ultimately, in that balancing process, what did I just introduce into the equation? I introduced H+. And what was H+? Acid. How do we monitor acids? pH. So pH can have a pretty drastic effect on our expressions because pH is monitoring H+ concentrations or OH- concentrations, and both of those things can show up in your equilibrium, or your chemical reactions. Okay, so pH can have a huge effect on your overall equations. Again, apologies for advancing so fast. Where did it go? There we go. And then we could also see concentrations affect. Why could concentrations go through an effect? What was the little side note, the little sidebar that we had written down? We had negative NFE equals negative RT ln K. Okay, and what is K? It's the concentration of the products over the concentration of reactants. So if we are at a non-equilibrium system, okay, which we'll want to be, but if we're at a non-equilibrium system, that can affect our overall expression. And that's where we're seeing Q come into this. Okay, we don't want to look at an equilibrium system because what's happening in an equilibrium system? They're the same. The flow backwards and forwards is the same, which means how many electrons are being transferred? They're the same, it's 0. So we're getting the same flow backwards as forwards. Net result is there is no flow of electrons. So we actually don't want to be at equilibrium. What we want to be at is off equilibrium, which is why we look at Q instead. So if you look at the expression that we've written up in the upper right-hand corner, this helps to set us up for systems when we're non-equilibrium. So within this equation, you've got R as your gas constant. Okay, again, the gas constant in units of joules per mole Kelvin. You've got your temperature, your number of electrons, Faradays, and then you get Q, which is your products over your reactants. Very similar to what we've done in the past. Okay. The neat thing about the Nernst equation is that if I had a cell potential, a standard cell potential of 0, could I still get a current to flow? Yeah. Okay, that's called a concentration cell. Concentration cells are very helpful if you're on a desert island. Okay, that's usually a good place for a concentration cell because what you can do is, why not, let's pick out coconuts. You can pick out your coconuts and line up a whole bunch of different concentrations of salt water. Okay. The salt water is going by osmosis, is going to flow to dilute or to dilute your strongest concentration. As the ions flow for that dilution, guess what else has to counterflow? Electrons. So you can create a saltwater battery to power things. Okay, do you get a lot of current? No, it's pretty weak. Okay, but if you've strung together enough of them, okay, in series or parallel, because I'm not an electrical engineer, okay, you could then set up and generate enough power to power a very small device. So you could listen to music if you had internet on this deserted island. Okay? So that becomes fun to be able to connect those. I will state the products and reactant concentrations have always tripped me up. So I would go back and make sure that I'm looking at my equations to ensure that I've got those aligned. Okay? Those, remember, are brackets. What did the brackets mean? Concentration, which means what is not going to show up, particularly if we tapped backwards to here. Our metals will not appear in our expression. All we're looking at is the concentration of the ions. That would be these guys. Okay? So, calculate your cell potential when the copper ion is 1.5 molarity and the zinc ion is 0.0002 molar at 298 Kelvin. What happens to the cell potential as reactants decrease and products, increase over time? So set up your expression. We probably want that Nernst equation. Since you all can go backwards better, this equals what? Our E standard cell. Was it minus? It was plus? Minus RTNF? Or did I do it backwards? That's right. And then natural log Q. Any kind of confirmation would be nice. Okay, thank you. So set it up and start your calculation and see what you come up with. I'm seeing a lot of people with numbers, so let's go through and start talking through some of this. So I saw a lot of people write down mostly what's written up here. I've got a few blank spots that we're going to talk about in detail, particularly because people keep missing it on quizzes, so let's pay attention to it. Okay. First and foremost, what is something that you were asked to include in your calculations? Units. How many of you actually wrote down any units?
None.
Yeah. Okay? So if you're not writing down the units, you can fully expect to miss points. Okay? In the grand scheme, that's not that big a point, a big a deal. If we look at just missing the units in one calculation, okay, that drops you to 9 points out of 10. That's still an A, and maybe that's all you care about. Okay? But I would highly recommend that that is a simple place to get points. So go ahead and make sure you've got your units in there. What are our units on R? Pen, come on. Joules per mole times Kelvin, 298. So that's convenient, those units cancel. What's the giant blank space now highlighted with purple parentheses? This was N, this is our number of electrons transferred. When we look at the overall equation, does the overall equation show any electrons? No. So it's up to you to decide how you want to go through and deal with that. One approach is you can go back. And actually, you can't do it on this one. You could go back and pull out a half expression or a half reaction. Copper goes to copper ion. To balance that out, what do you need? You need electrons. Where should we place the electrons? Sure, we can place it on the right-hand side of the equation. Did my charge get closer to being balanced or further? This is a +2 equals a -2. It initially started at 0, which means I screwed up. Okay? We need the electrons placed on the correct side of the equation. That would balance that out. Which means for the copper ion to turn into copper metal, how many electrons do I need? 2. Okay? It is something that you should cross-reference to ensure that the zinc also matches. But if you go through and look at the zinc, you'll see that the zinc does indeed match. Zinc going to zinc +2. I need to cancel that +2 by adding 2 electrons. The electrons cancel out, which means our N is 2. 2 what? Moles of electrons. What was Faraday's constant? Say again? I think it was. I was going to say coulombs per mole. Okay. Can we get a cross-reference on that? Okay. Okay, and you can tell I don't have it memorized, which means what should you do? Write it down. You can memorize it, but I would argue you should just write it down on your cheat sheet so that you've got it. Okay, so that way when you go through to use it, you know to include that unit. We're not showing any units in the Q. That gets a little bit dodgy, but for the most part, we ignore those units. Does anybody know why? That was a bad question. I shouldn't ask that because that's a lot more advanced. If you have to move into more advanced either chemistries or chemical engineering, okay, then you would encounter what K actually is, and it's not molarity. Okay? It's something known as activity, and that's why we've ignored units when we look at K. Okay. We could then go through, punch it all into the calculator, and assuming at least the front table is correct, we get 1.19 volts. Which might look a little bit weird because if we look at how our units cancel, how is joules per coulomb equal to volts? It is, actually. That was the whole point of that conversion process. A joule per coulomb is equal to a volt. Okay? That's the point of that unit system. That's why we set it up that way. So I believe we're getting a positive 1.19 volts. Okay? Second part of the question. What happens to the cell potential as our reactants decrease and the products increase over time? Does it make sense for our reactants to decrease and our products to increase over time, or should it have gone the other way? How would we know? What was the standard cell potential? Positive or negative? Positive, which means this reaction was spontaneous, which means we are increasing the products over time. That's what that spontaneous reaction means. Okay? So what happens to our cell potential? How would we figure that out? Okay? If you're like, I don't really know, then pick some random numbers. Okay? If the products increase, don't use 0.002. What should you use? How about 0.1? Okay? So our products increased. We need our reactants to decrease. So pick a smaller number. Okay? You could just pick 1. Recalculate and see what happens. What do you think should happen? The cell potential should go down. Why? Why are the products increasing and the reactants decreasing? Le Chatelier's, decent idea, because we're not at equilibrium, right? So what's happening is our products increase and our reactants decrease so that we can get our Q to become a K, to reach that equilibrium point. And what happens once we reach that equilibrium point? The rate of the forward equals the rate of the reverse, which means, is there a net electron transfer? No. And if there's no electrons being transferred, what's your cell potential, also known as the flow of electrons? 0. Okay? So your cell potential will drop until you've achieved that equilibrium. Once you're at that equilibrium, the whole thing shuts down. Kind of, sort of? Okay. How does that manifest in the real world? You get a dead battery. Put in the battery, it works. Why? Because you're not at equilibrium. We've controlled that reaction to not run until it's in a circuit. Once it's now in a circuit, the reaction is actually cycling. We're gradually increasing the products and decreasing the reactants as that reaction runs. Eventually, it reaches a point where the reaction is no longer spontaneous in the forward direction. And if it's no longer spontaneous, there's no net flow of electrons, you get a dead battery. Okay. Do we ever actually achieve that with batteries? Does anybody actually know? It's a real easy test. The next time you have a dead battery, if you've got a multimeter, which I would highly recommend, okay, attach a multimeter to it, and what you'll find is they still have juice in them. Okay, they still have electric flow going in them. It just happens that the device that you're using requires more electric flow than the battery can supply. Okay? And it's usually a very disappointingly small differential if you haven't played around with it. So, how do our batteries work? They flow from your anode to your cathode in a spontaneous redox reaction. Okay, what's happening at the anode? Oxidation. Okay, how do we know it's oxidation? Thank you for mouthing it. Anox. Okay, so we've tied the anode to oxidation, and what's happening with an oxidation? Leo, loss of electrons. So what's happening at the anode is our electrons are flowing out of the anode towards the cathode in a spontaneous reaction. Okay, since they're flowing, that flow we can attach to a wire or a load, and we'll get our moving electrons. Okay, there's an electrolyte within the battery that helps or acts as a salt bridge, and then once all of those reactants are used up, our reaction stops flowing. Okay, and our battery is dead. Again, most batteries actually still have a significant amount of electrical current still in them. It's just not enough to power whatever device you're working with. So an alkaline battery contains electrodes made of zinc and manganese. So we've got these two reactions. Write the overall spontaneous redox reaction that occurs and calculate the value of the cell potential, which is the anode and which is the cathode. What kind of half reactions were you given? Said differently, are you given the correct half reactions for the cell potential? No. Okay, to get correct half reactions, we would need one that was oxidized and one that was reduced. How do we decide what was oxidized and reduced? Gain and loss of our electrons. So if we focus on our reaction arrow, the electrons are both on the reactant side, which means we are looking at, in both of these cases, the reduction potentials. They're gaining electrons. So what you have to go through and do is to flip the correct equation to get your cell potential, your standard cell potential. Once you've got your correct equations set up, that will help you also determine your anodes and cathodes because you've memorized anox and red cat. Swing away. So let's go through and talk through this. We encounter some questions about what we're trying to go through and do, like what is our objective. Okay, so first and foremost, if we're looking at a battery, okay, what's the point of the battery? Generate electricity. Okay, so for it to generate electricity, for it to not be a dead battery, what should the cell potential be? Positive. Okay, so I can look at all the equation stuff, but I'm actually going to ignore all of the equation stuff and just zero in on the cell potentials, or rather my reduction potentials. Okay, so if I want a positive, what happens if I flip that top equation? I'd get a negative 0.15, right? So what I'm saying is I'm going to take that top equation and I'm going to flip it. Instead of running the reduction, I'm going to run the oxidation. To get my cell potential, I would add that new number to the other number. What value do I get? Negative. Is that what I want my battery to be? No. So what does that mean? That was the wrong thing to do. So let's go through and take a look at the other one. What if I flip this one? My cell potential becomes positive 1.28. Okay? And I keep calling it cell potential, the reduction potentials. My cell potential is now the additive process of those two equations, which then means I would have a positive value. I'm not even stressed about the number yet. I'm just trying to decide the magnitude, the favorable magnitude. Everything we're trying to do is generate a positive cell potential. That is our goal. Right? We're trying to generate electricity. And if I'm going to go ahead and flip that one, that means I need to flip this equation. So I would rewrite that equation. Zinc plus 2OH minus would now go to zinc oxide plus H2O plus 2 electrons. What am I going to do to the other equation?
Keep it the same.
I'm not going to do anything to it. I'm going to keep it the same. 2 electrons plus H2O plus 2 MnO2. That goes to my Mn2O3 plus my 2OH minus. Okay, what happens? My electrons would cancel. That's fantastic. That's what I want. I could go through and look at my cell potentials, remembering that I had flipped, or my reduction potentials. Dang, can't fix that. Okay, that was plus 1.28 volts because we flipped the equation. The other one we left alone, so 0.15 volts. I could look at my E cell. Would be equal to 1.28 plus 0.15, and I get a number larger than 1.28? 1.43 volts. Okay. If I was just asked for the cell potential, I'd be good, except it asked for the overall redox reaction, so I'm going to have to go through and add these two things up. Okay. Depending on how you want to approach this is kind of up to you. You'll note that I wrote all of these equations out. I flipped so that I could see these systems. Okay? I flipped so that I would actually be able to navigate the kind of mathematics for the overall cell potential. Because what do we see happening? I get 2 hydroxide ions on the left and 2 on the right, which means those will cancel. What happens to the water? The water also cancels, which then means I get zinc plus the 2MnO2. This goes to the zinc oxide, plus the Mn2O3. Make sense? Okay, so I now have a proper overall equation for the spontaneous reaction. I've got a cell potential. What's the anode and which is the cathode? For me personally, An-ox. An-ox meant loss of electrons. Which equation lost electrons? The zinc one, so I would argue my color coding sucks. This was my oxidation, and that meant this was the anode. And then the other one had to be my reduction because it gained electrons, and then that would be my cathode. Make sense? Questions? Okay. Again, the key point that starts this whole process off is what is our goal? Okay, when we're talking about batteries, we want positive cell potentials. That is the whole point. Okay? Questions? Okay. So battery voltage decreases over time as our reactants get used up. Okay, so what we see here are our curves, okay, are our voltage curves, and you can see how your voltage drops. You're seeing this threshold line. I'm not positive for that threshold line, but that threshold line might very well be where we've actually hit dead battery. Okay, so that when we're looking at this plot, as soon as that curve crosses that threshold, we're no longer a useful battery, and people would then be throwing it away, even though it still had current stored up in it. Okay? So your voltage is going to decrease over time. I didn't update really any of that. Well, I cut the office hours. I do not believe there's another Alex homework. Okay? Based on what I'm seeing within Alex, there's nothing there. So you shouldn't have to worry about another Alex, but there is a paper homework. Okay, so please pay attention for that. And then also, I'm not going to be on campus this Friday. It's kind of an important note. So redox reactions play an important role in biological systems. So you can go through and look at a variety of different cycles, and what we'll end up seeing is that we get lots of electron transfer throughout biochemistry processes as well. Okay? So we want to understand what's going on within those just as much as we want to understand what's going on within batteries. Because if we can understand why electrons are being transferred in biological systems, we could enhance or we could try to fix diseases that have problems with those electron transfer pathways. Okay? You'll see common molecules NAD+ will switch to NADH, FAD to FADH2, and those will act as oxidizing and reducing agents in those individual chemical reactions. Those reactions are doing the same thing as batteries, right, but it becomes a little bit nuanced in how we go through and interpret those. All right, so if we go through and look within the citric acid cycle, we're going to change oxaloacetate to malate. Okay, and the question becomes, how do we go through and do it? So we've got cell potentials monitored for these because we can study them and come up with those cell potentials, but those are not going to be your standard things that you would find within your textbook. These are going to be now secondary reactions. So write the overall reaction and calculate the value for your cell potential to see if the reaction is spontaneous. So we're switching malate is oxidized to oxaloacetate. Okay? That's the question, or that's our equation that we're trying to do. If that's our equation, what is the malate? Reactant or product? Malate is oxidized to oxaloacetate. Does that sound like a reactant or a product? We've got one person saying reactant. Everybody agree? go for it. We'll talk about it in a second. Set it up. So let's talk through this. The first statement that was made, because I asked, should malate be a reactant or a product? And I heard the first statement was, should be a product. Okay, I believe that's what I heard. Did I hear that right? Yeah. Okay, so if we're going to go through and run that, we're just going to go kind of blind on this and fast, and we'll see why here in a second. Plus 2H plus 2 electrons goes to the malate. Okay, so that's going to give us a cell potential of negative 0.166 volts. Okay, if that one is going to happen that way, what has to happen to the other equation?
Flip it.
We got to flip it. Okay, so this is going to go to NAD plus H plus 2 electrons, NADH. And if we flip it, what happens with our cell potential?
Reverse.
Say again.
It flips, it's positive.
It flips, so we have our negative 0.320 volts, but we now make it positive because we flipped that equation. And we could add those two numbers up, and we'd get a magic number, and our magic number is ballpark 0.15 volts. Is the reaction spontaneous? Yes, we have a positive cell potential. That's all well and good. And as far as this, if this equation or question was on a quiz, this would net you about half credit, maybe a little bit more. Whoa. But we did it all right, didn't we? What did we do wrong? We didn't read the question. The question says malate is oxidized. Malate's a product. Malate isn't oxidized. Malate would be the product of the oxaloacetate being reduced. Which, while all these equations and the mathematics are all lovely and fantastic, that's grand. You didn't answer the question. Okay? So what does that mean we have to do? Go back and answer the question. Malate is oxidized, and I would argue the operative word, which is why I circled it, was 2. Okay? Malate is oxidized 2, or malate 2 oxaloacetate, which means malate is a reactant. What happens to the cell potential? If we look, we were given the reduction cell potential, it gaining electrons. In this case, it lost electrons, which means what do we have to do to the cell potential? We have to flip that sign. So it started as a negative 0.166 volts. I need to make it positive. Okay, since I flipped that one, what do I do to the other one? Keep it the same. NAD plus 2H plus 2 electrons, 2 NADH. That cell potential we do nothing with, and we get what happens? A negative 0.154 volts. I'm trusting your numbers. Okay. So this question becomes different. When we think back to what we did with the batteries, what was our assumption or our underlying process for calculating batteries? Spontaneous. I wanted to see a positive cell potential. When we shift into the biological systems, we're not necessarily going to see a positive cell potential. Okay? So you have to be careful in your underlying assumptions. You have to phrase it based off of the way the question is asked. Does that make sense? Okay, so we do have to watch that very, very carefully and navigate this. Make sense? Okay. So another one, calculate the cell potential for the reaction at 37 degrees Celsius and pH 7 when the reaction, or when the ratio of any, oh my goodness, and the concentrations of malate and oxaloacetate are equal. Okay, H plus is the same thing as H3O plus. All right, so we want to go through this same process now. All right, we're going to need some numbers from the other side. Does anybody have those numbers memorized?
Yeah, it's negative 0.166.
Oh, and actually, previous slide was our malate oxaloacetate, which is what we just went through and did, right? So what was the cell potential for that? negative, come on, 0.154 volts. So we just ran that calculation on the other side, so we'll need that cell potential to calculate this. Okay, so now we've got a new question. We want to calculate the cell for the reaction, 37 degrees Celsius, pH 7, all this fun stuff. What do we need? What do we need to be able to figure this out? Say that again? Nernst. Sorry, I keep hearing Hertz. The Nernst equation. What was our Nernst equation? E cell equal to E cell, not, it's not on this, is it? No. Minus?
Gas constant times temperature over electron transfer Faraday's constant. Natural log Q.
Okay. So you've got some different pieces that you've got to go through and process. See what you can come up with. Actually, let's talk through it again a little bit real quickly. Let's take a look at the Nernst equation. What parts of the Nernst equation do you know? RT, F, Q? Do you know Q? Q is a little bit tricky. I would argue that's the one that's going to hold you up. And then we have our standard cell potential, which I didn't include the cell, but we do have that cell potential. Do we have N?
Yeah.
So we said yes. We got a no in the back. Why are you saying yes up in the front?
You can just find it in the previous one, right?
Yeah, go to the previous slide where it actually showed the number of electrons. Okay, that's how you're going to pick that one out. Okay, which I think was 2.
Yeah.
Okay, 2 electrons. So the real question here is what's going on with Q? So spend some time, talk to your tables, figure out what's going on with that. Okay, I think the Q is really stumping a lot of people. How do you solve for Q? So let's try actually a slightly different thing that I'm probably going to regret, but I'm going to do it anyway. How do I solve for Q? Products over reactants. What are your products? Oxaloacetate, yes. NADH. H plus. What are your reactants? Malate and NAD plus.
Yeah.
Did you write that down?
No.
Okay, so if we just go based off of how we know to calculate Q, Q is your products over your reactants, so we get the oxaloacetate. Nobody wants to write out oxaloacetate, that's fine. NADH, H plus, right? All over, concentration of malate, no one wants to write that out. NAD plus, and that was it, right? Right. So I got lots of people telling me Q was 1. Where did 1 come from? Okay, I got another group of people telling me it's 700. There's at least a 700 in the equation, so I can kind of go with that. There's actually a 1 in the equation too. Where did the 1 come from? We know the concentration of oxaloacetate and to the malate is 1. The products are equal. So Q, yes, has 1 in it. That's fantastic. Okay. Do I know the ratio of NADH to NAD plus? Yeah? What was it? Sort of. 1 over 700, because the ratio I was given was NAD plus to NADH. I need NADH to NAD plus, so that's 1 over 700. Oh, and then H plus. I wasn't given the H plus concentration, was I? I was told that I have a pH 7, and I know the pH 7 equals the negative log of the H plus concentration, which means I now know that the H plus concentration is... Hopefully you're not retaking quiz 3. 10 to the negative 7. Sorry, that was a little bit of salt. That was a little saltier than I intended to be. Okay? If you are, you should go back and review. Make sure that you know how to get your H plus concentration from the pH, which then means 10 to the negative 7. Do you know what Q is?
No.
You've got all those numbers. Plug it all in. See what happens. Okay? That's what you're now being asked to navigate and do. I genuinely don't know the number, but that is a lot of math to kind of go through and do. It looks like, so ooh, you had a calculation. Did you get it?
Yeah.
The whole thing? RT and all that?
Yeah.
Cool, look at that. And we got a cell potential according 0.1422. Okay, that would be positive, hopefully. Right? Why is this special to us? Why do we care? What's going on behind this? If we look at the conversion of malate to oxaloacetate, this is something that has to happen within the Krebs cycle. I know, biology, who cares? But it's happening in our biological systems. It's happening inside us. It's how we generate energy and all of that kind of fun jazz. And if we look at just the cell potential, what happens? Nothing. The reaction does not happen. Because if we evaluate the cell potentials, we get a negative value. That means that reaction does not occur. Okay? That's a problem considering that the whole point of the Krebs cycle is that it continues to cycle. It must occur. Okay? So why is it occurring? Well, the why it's occurring has to go back to the concentrations of each of these individual species. Okay? The oxaloacetate and the malate we're saying is one. Why are they both present? Well, if we're looking at a Krebs cycle or a citric acid cycle, I think I've got that right, and we're looking at that conversion, the concentrations of each of those species stays relatively constant. Okay, we're looking at minor fluctuations that cause it to continue around. Okay, which means, for the most part, the ratio of oxaloacetate to our malate concentrations is about 1. The ratio of our NADH to NAD plus is going to be significantly different. Okay? That's going to be dependent on the activity of those. NADH is a very reactive molecule, which means we don't want a lot of that floating through our stream. We only want to use it at the points where it's important, which means when we look at that ratio, we get a very small amount of NADH present. And then the last factor within our puzzle is the concentration of hydrogen ions, our pH. Okay? So all of those things now factor in to contribute to now making the cell potential that was a non-spontaneous reaction, did not want to happen, to now all of a sudden, ta-da, now it's positive. Now our reaction actually cycles. We can explain why that reaction occurs using the Nernst equation. That's pretty neat and powerful. Okay? To anybody that has any passing interest in what's going on in biological systems. Okay? Extra bit of stuff that becomes fun within this is how does the cell potential change if the pH is decreased? Okay? Remember, Unit 3, when we talked about acids and bases, biological systems really wanted a neutral pH or a stable pH. This is why we had buffer systems, to maintain the pH in a narrow range. Because what happens if we swap outside of that range? Well, we'd initially talked about, or we could look at, was intermolecular forces change. We can denature proteins. We can destroy things. We could also look at how the solubility of individual ions changes through a chemical reaction. And we can now also see how the H plus concentration can affect the value of Q, which is going to affect whether the reaction actually occurs or not. Right? How would we decide how the cell potential changes? Right? Well, if the pH decreases, what happens to the concentration of H plus? It goes up. So what can I go through and do? Instead of being 10 to the negative 7, let's make it 10 to the negative 6, negative 5, negative 3. Recrunch the calculation and see what happens to your cell potential. Should be really easy, right? Got it saved in there?
It decreases.
Cell potential dropped to 0.08,
I did it for the power of -5 though.
negative 5. So if our pH decreases, if we become more acidic, what happens to our cell potential? It becomes less likely to occur. Right? So we could use fluctuating pHs to monitor or change the effectiveness of how the Krebs cycle functions. That's pretty cool. Right? By just playing around with the concentration of H+ ions. A single atom's presence can change whether we survive or whether we die. That's kind of cool. And really scary. Kind of makes sense? Okay. So cells, concentration substances are tightly regulated, and I should just shut up because we're done. So I'm going to click stop.